There is a moment before every great journey when nobody is watching. Not the cameras, not the crowds, not the world holding its breath for a launch. It happens earlier than that in a quiet room with quiet people looking at a problem that has no clean answer. And what they decide in that room with no applause and no countdown is what truly shapes history. This is a story about one of those rooms. It is a story about the path to the moon, and how recently that path took a sudden, dramatic detour, one that almost nobody outside the program noticed at first, but one that changes what the next great rocket flight really means. Let me take you there. For years, the plan was simple in its ambition. Build the most powerful rocket, put astronauts on top, send them around the moon down to the surface and bring them home, one mission, one enormous leap. That is the dream version, the version on the posters. But dreams have a habit of meeting reality somewhere along the way, usually in a hallway, usually carried by an engineer with tired eyes and a folder full of numbers. And the number that mattered most was a small one, not the size of the rocket, not the distance to the moon. The number of pieces left. Deep inside the Space Launch System, the giant rocket meant to carry the Orion spacecraft sits an upper stage. Think of it as the second push. The first stage roars off the launch pad in fire and thunder. Then this smaller stage takes over quietly in the dark above the atmosphere and shoves the spacecraft toward the orbit it needs. It is called the Interim Cryogenic Propulsion Stage, a cold, technical name for a piece of hardware that was never meant to last forever. The ICPS is based on the upper stage of the Delta IV rocket, and that line of hardware has been discontinued. Discontinued, such a small word for such a large problem. Because the replacement, a newer, more capable upper stage, is still being adapted for the SLS missions that come after. Which left NASA standing in that quiet room, looking at a shelf that was nearly empty, holding one of the rarest pieces of hardware left in the entire program, and asking themselves a question that no engineer ever wants to ask out loud. Do we spend it now, or do we save it? Here is where most stories would show a dramatic argument, raised voices, a table slammed, somebody walking out. The truth is usually gentler than that, and somehow heavier. The decision they reached was almost absurd if you only hear it in one sentence. They chose to fly the giant rocket without its working upper stage. In its place would go an inert spacer structure built at Marshall Space Flight Center, a hollow adapter instead of a functioning rocket stage. Sit with that for a moment. Replacing an engine with an empty shell, on purpose, on a mission carrying human beings toward the moon. It sounds like a step backward. It sounds like giving up something. And in a way it is, but not in the way you might think. Without that powered upper stage to carry it the rest of the way, the Orion spacecraft must now rely far more on its own propulsion, finishing the job itself, performing the orbital maneuvers the rocket stage would normally have handled. The ship would have to do more, carry more of its own weight, prove that it could. And that, quietly, is the entire point. This was never about wasting hardware on a single triumphant flight. It was about a full-scale rehearsal, without spending the one critical piece they could not get back. They were not weakening the mission, they were redefining what the mission was for. The old plan tried to do everything at once. Launch, travel, land on the moon, return, the full song performed perfectly on the first night. The new plan is humbler, and because it is humbler, it is wiser. NASA stopped trying to validate everything in a single mission. Instead, the focus narrowed to one thing above all others, proving that Orion and the commercial landers can rendezvous, dock, and operate safely together in orbit. Not the landing, not the footprints in gray dust, just the meeting, two spacecraft far above the Earth finding each other in the dark and joining hands. The harder milestones, life support, the long engine burns, full habitation, those can wait, until the orbital systems first prove they can be trusted. There is an old principle in this world, repeated so often it has worn smooth like a stone in a pocket. Test like you fly. It means running your tests under conditions that mirror the real mission as closely as possible, to shrink the risk, and to prove the hardware before the moments that cannot be undone. So they built a realistic version of the journey. Orion placed in a stable low orbit, roughly 463 kilometers above the Earth, tilted at an inclination near 33 degrees. There, the crew would meet a commercial lander, perhaps Starship, perhaps Blue Moon, and begin practicing the exact choreography that every future moon mission will one day require. If this all feels familiar, it should. Decades ago in 1969, Apollo 9 did almost exactly this, testing the lunar module for the first time in Earth orbit, validating docking and navigation and crew transfers all before anyone dared to attempt a landing. History does not repeat, but sometimes when the stakes are high enough, it remembers. And here is where the story turns, the way a camera slowly pulls back to reveal something larger than the frame you were looking at. Because all of this, the empty spacer, the narrowed mission, the careful rehearsal, places an enormous weight on a single, separate flight. A test flight. Currently scheduled for May 19th, it is expected to introduce the Starship version 3 architecture for the very first time. Until now, the test flights were mostly about the violent parts. Launch, re-entry, fire on the way up, fire on the way down, but version 3 shifts the whole story, moving Starship away from just surviving the climb and toward actually working in space. Suddenly, this is not just another test. It becomes the proving ground for the systems the entire revised moon plan now depends on. The validation in the real cold of orbit for the docking and the cryogenic systems that have to work. A single flight quietly carrying the weight of a decision made in a quiet room. Let me show you what is at stake on that flight, not in numbers but in feeling. Along the side of the ship, 4 docking drogues are mounted, the physical interfaces that let one spacecraft connect to another. The system is designed to be androgynous. Either vehicle can be the active one doing the maneuvering while the other waits, passive, like 2 pieces that fit together no matter which hand holds them. But the connector is the easy part, the hard part is the approach. A spacecraft moving at orbital speed must know its exact position, its orientation. Its closing speed relative to the other ship, because tiny errors can turn dangerous when 2 massive vehicles try to meet in the silence of microgravity. So the ship leans on proven navigation sensors, supported by roughly 50 cameras spread across its body, together forming something like a 360-degree field of vision, always watching the distance closing. Then there is the strangest problem of all. A spacecraft must know its own weight, and most of that weight is propellant. On Earth, measuring fuel is simple because gravity pulls the liquid to the bottom of the tank. In space, there is no bottom. The fuel floats free, forming drifting blobs spreading along the walls without warning. The answer is quietly beautiful. Instead of physical floats, the system sends radio waves into the tank and listens to the echoes, and from how the signals bounce, it builds a real-time 3-dimensional map of where the fuel actually is. A fuel gauge designed for a place with no down. And the final piece is the gentlest. Older ships use simple cold gas thrusters. Version 3 reaches further, using cryogenic propellants, supercooled methane and oxygen, far more powerful, but with one cruel flaw. If the liquid warms, vapor bubbles form inside the system. Bubbles in a thruster are like air trapped in a car's brake lines. Instead of smooth, predictable force, you get sputter and unevenness, exactly what you cannot afford during a delicate docking. So a high-voltage pump runs constantly, circulating and cooling the propellant like the liquid loop inside a high-end machine, keeping it cold, stable, and free of bubbles. And the result of all that, the cameras, the radio echoes, the relentless cooling, is one quiet, almost tender outcome. Not rough bursts of thrust, but tiny, carefully measured pulses, precise enough to guide an enormous spacecraft into contact with something close to feather-like gentleness. A machine the size of a building, reaching out, as gently as a hand finding another hand in the dark. So we come back to the quiet room. To the empty shelf and the rare piece of hardware, and the people who chose not to spend it on a single perfect moment. It would have been easy to fly the dream version, to chase the headline, to put everything on one flight and hope. The earlier era of spaceflight accepted risks that would simply not be acceptable today, especially for a program this large and this complex. Instead, they chose patience. They chose to rehearse. They chose to prove the small, unglamorous things first: the hatch, the handshake in orbit, the gentle touch, and to let the giant leap wait until the ground beneath it was solid. There is a kind of courage that looks like boldness, fire and thunder and a rocket tearing into the sky. And there is another kind, quieter, harder in its own way, the courage to slow down when everyone expects you to rush, to save what you cannot replace, to say not yet but soon and properly. The path to the moon took a detour. But a detour chosen carefully by people staring honestly at what they have and what they cannot afford to lose is not a retreat. It is just the longer road, taken by people who intend to arrive.